Hi there, welcome to the fifth and final video in logs and exponentials. Today we're just going to look at a couple of examples with graph transformations. Okay, so we've done graph transformations as part of the functions and graph topic, but I'm just going to take you through a couple of examples looking at the kind of specific quirks to do with log and exponential graphs. Okay, so two things you need to do: be able to identify transformations of exponential and logarithmic graphs and able to sketch them basically. Now, as a reminder, these are your logarithmic graphs. Okay, remember you've got your exponential graph. If you've got y equals a to the power x, we know these always go through the point 0, 1, because when you make x 0, anything to the power 0 is 1. And we know they also go through the point 1a, because x 1 a to the power 1 is just a. The inverse graph here, the logarithmic graph, is y equals log x to the base a. And we know those points are just switched around. So instead of being 0, 1, it's 1, 0. And instead of being 1a, it's a 1. Okay, now just one more thing that we talked about before. There is what we call an asymptote here. That graph approaches the x-axis but never ever touches it. And then the same here for the log graph, apart from the fact that it's a y-axis. Okay, it'll never ever ever touch the y-axis. It'll get closer and closer but never get there. Okay, so take a wee pause of the video and have a look at these and see if you can find the equations of them. Okay, now first things first, these equations are log equations. Okay, and a lot of the time they will be in the equation, the form of the equation will be in the question anyway. Let's call it log a to the power x minus b. Okay, now firstly what we should be noticing here is that they have moved. They're a transformation of a log graph. Okay, so in this case here, this is at 5, 0, whereas we know that should be at 1, 0. Okay, so if it should be at 1, 0 and it's now at 5, 0, the whole graph has moved to the right 4 places. So we know our log graph is going to be log A, and there's going to be minus 4 inside the bracket to move that right 4 places. Okay, then there's a couple of ways of thinking about getting that base. We need to know the base as well here. You can either think about it in terms of, well, if it's moved 4 places to the right, where did that 7, 1 start? And what does that mean? Or what you could do is take your 7, 1 and just substitute it in. Okay, which I think is my better method, because when it starts being 1 in the y-axis, like over here, this method will still work. So if we sub that in, 1 is equal to log to the base a of 7 minus 4. Okay, so 1 is equal to log a 3. Okay, and then you can solve your log equation. A here has to be 3. Okay, because you know if the log gives you 1, the base matches what's beside it. Okay, so a is 3, and your equation, okay, just to give me I'm just going to put it up here just to give me a little bit more space. Your equation for this graph is y equals log to the base 3 of x minus 4. Okay, that's your equation. Okay, so the second one here, a little bit different. We're not told where it cuts the x-axis, we don't know that point, but we do know that this asymptote, this log, is approaching the line y equals -3, or x equals -3 rather, instead of the y-axis. Okay, so we can see from this graph that it's been moved left 3 places, which means you're dealing with log to the base a of x plus 3. Okay, then we can substitute the point in. Y is equal to 3. Log to the base a of 5 plus 3, which is 8. Okay, now we're solving this equation. Now this is a little bit more involved, not as easy as this one. So let's put a phantom log, or introduce a log in here. It's going to be log a to the base a is equal to log 8 to the base a. Your power comes up, log a to the base a cubed is equal to log a8. So a cubed is 8, which means a has to be 2. So your graph here is y equals log to the base 2 x plus 3. Okay, so just transformations, working with log graphs, a couple of little quirks. You need to really know your logs and your exponentials. Okay, example 2 here, graph of the form y equals 3m to the power x, find the value of m. Okay, we'll give it a wee try. Y equals 3m to the power x. Again, same as any graph, we can take our coordinate and turn it into a point. or take a point and turn it into a x and y value. So the y value here is 12, 3m, x is 2, so we're just solving that equation. So 4 is equal to m squared, so m is equal to plus or minus 2. In this case, p has to be m has to be 2 because m has to be greater than 0. Okay, otherwise it has to be greater than 1 actually, because we know from the graph that it's going that way. That's the form when m is greater than 1. Okay, so m is equal to 2. Okay, and then just two last wee tricks of the trade here, particularly log graphs. They're very difficult to sketch if we have the 3x in there beside the thing. We pretend to look at it. It's much, much easier to look at it in terms of the basic log graph, log x to the base of something. Okay, so what we're going to do is we're going to turn these into a version of that. Okay, here we've got log 3x to the base 3. Okay, I want that in terms of the log x to the base 3 basic log graph, because if I can do that, it's much easier to transform. Now what I can see here is in here we've got a multiplication. Now if that's a multiplication, that means that came from two logs being added together. So log 3 to the base 3 plus log x to the base 3. And we know that log 3 to the base 3 is just 1. So this is log x to the base 3 with an extra 1 there. Okay, so rather than having, and you can do it, but rather than having the 3 in there causing us bother, we can just do this as a basic log graph shifted up one place. So my graph here, my basic log graph is going to go through 1 and 3, 1, because we're talking about log x to the base 3. Okay, so I'm going to do the same graph, but move one place up. Okay, so it's going to come up here, and it's going to go through, instead of 1, 0, it's going to go through 1, 1. Instead of going through 3, 1, it's going to go through 3, 2. Okay, so you can see how a little bit of manipulation with your logs there will really help in drawing that graph. Same with this one here, y equals log 1 over x to the base 5. We can see there's a divide in the subject there. So that's going to be log 1 to the base 5 take away log x to the base 5. And because if we've got a divide, we know that has to be taken away with logs. And then we know log 1 to the base 5, that's just 0. Okay, because anything as well as 0 will give you that 1. So we're really just doing y is equal to minus log 5 to the base x, which again is much easier because well, I know what my basic log graph looks like. It goes through 1 and it goes through 5, 1. And I also know if I make something negative at the front outside of the x, away from the x, it just flips it in the x-axis. So I'm going to have exactly the same graph, but upside down. So going through 1, 0, and then going through 5, negative 1 instead. Okay, now this was just a little video just to show you a couple of quirks when it comes to transformation with logs. So being able to identify transformations of exponentials and log graphs and being able to sketch them is the two things we're looking to do. Okay, thank you for your time.